Welcome to Summarize Science. Ever wonder if a robot actually understands your commands or if it is just guessing based on what it sees? A groundbreaking new study has performed a mechanistic deep dive into the brains of vision-language action models, the AI systems that power modern versatile robots. These researchers analyzed 6 different AI architectures, ranging from 80 million to 7 billion parameters. They conducted over 394,000 rollout episodes across 4 major benchmarks to see how these robots process information. One of the most significant discoveries is that the visual pathway almost completely dominates a robot's behavior. In many cases, the visual scene is so influential that the robot's brain already knows what to do before it even hears a command. The study used a technique called activation injection to prove this. By taking the brain signals from one successful trial and injecting them into another, they could force the robot to follow a specific path regardless of the new situation. Interestingly, the researchers found that language sensitivity depends more on the task than the AI's design. If a robot sees a single object it is trained to interact with, it often ignores the language prompt entirely. For instance, if there is only one bowl on the table, the robot might pick it up even if the command is left blank. Language only really becomes essential when the scene is ambiguous. When there are multiple different objects or goals visible, that is when the robot finally checks its language centers to decide which one to focus on. This reveals that robots are often following spatially bound motor programs. Instead of understanding an abstract concept like cleaning, the robot is actually tied to specific coordinates in the physical space it sees. The researchers also found that these AI models have specialized pathways. Think of it like a division of labor. Some parts of the neural network encode what the goal is, while other expert pathways focus purely on how to move the arm. To make sense of these complex signals, the team used sparse autoencoders. These tools act like a translator, turning dense mathematical data into interpretable features that humans can understand. Through this method, they identified over 82 unique manipulation concepts, such as putting, pushing, and interacting. This allows us to see exactly which neurons are firing when a robot recognizes a bowl or prepares to grasp a handle. They even visualize these features in action, showing how a robot's plan can be disrupted if certain concept signals are zeroed out. If the opening concept is blocked, the robot might reach for a drawer but fail to actually pull it open. The study also looked at how different AI models compare in their overall capabilities. Some models are much better at following complex, multi-step instructions, while others are more robust against visual distractions like changes in color or lighting. To share these findings with the world, the researchers released the Action Atlas. It is an open-source platform that allows anyone to interactively explore how these different robots represent the world around them. In summary, this research proves that while robots are getting smarter, they still rely heavily on visual cues over deep language logic. Understanding this visual dominance is key to making robots that are safer and more predictable. This study provides a vital toolkit for diagnosing robot failures and improving how they learn. In the future, this could lead to AI that truly understands the nuances of human instructions in any environment. Thanks for watching Summarize Science.